Thank you to the organizers, Shreyash, Jeanette, Mangji, Marco, for hosting me. I'm really excited to come here in person. I come from Pittsburgh all the way here to just give this talk and meet all of you. So yeah, as Jeanette mentioned, I'm Sanjiban. I am currently a research scientist at Aurora, where we do self-driving, which I'll talk about today. I'm also joining Cornell as assistant professor in July 2022. So if you're a prospective student, reach out. Today, I'm really excited to talk about interactive imitation learning. Sort of how do we build robots that learn from human interaction and plan alongside humans? And in the spirit of this lecture, if you have any questions, this is an interactive session, so please feel free to ask. All right, so let's get started. So the question at the core of my research is, how do we design robots that both understand and learn from natural human interactions? For those who have seen this movie Baymax, this will be a familiar scene where Hero teaches Baymax to do a fist bump. What's beautiful about this scene is that Hero, through a simple sequence of interactions, is able to communicate this novel concept of a fist bump to Baymax, right? So how do we build such robots that continually improve and learn online to adapt to individual human preferences? Now, to do so, I think we need to solve two fundamental challenges. First, how should robots learn from natural human interactions? Consider this case where your grandma receives a brand new robot apprentice. There are a number of tasks she wants the apprentice to do in a specific way, but that's latent in her mind, right? How can the robot interact with her to infer these latent preferences from natural modes of feedback like gestures, interventions, or corrections? Second, how should robots plan alongside human partners to accomplish these tasks? The robot must be able to anticipate how humans respond to their motions, understand their intent, and move in a safe, predictable manner. Okay, so for the past 2.5 years, I've been working in self-driving at Aurora with an amazing team led by Drew Bagnall. Our key product is the Aurora Driver. This is a general suite of software that's designed to work on any vehicle, from passenger sedans to Class 8 trucks. Now, you may be wondering, what does this hunk of steel have to do with humans? Right? The answer is actually a lot. Let me show you. So this is a hyperlapse of the Aurora Driver hauling goods in Texas without any human interventions. It's really fascinating to see this robot drive like a human alongside other humans in the road, in the real world, engaging in novel interactions like merges, lane changes, stop signs, unprotected left turns, and much more. And keep in mind, these are negotiations that the robot is doing with real humans in the real world. Now, this is not a one-off result. Our product is hauling goods for FedEx every day. It's pretty cool that in just 9 months, we went from never driving on a truck to this result. So what is the science behind this result, right? That is what I'm here to talk about. Well, let's begin by looking at any one snapshot and ask, what is the optimal action that the robot can do in a situation? Now, you might think, like myself in the beginning, why not just take the official driving handbook and apply that, right? Well, that would not be very useful because most of the rules of driving aren't explicit, but rather implicit. This orchestrated chaos that you see is what I call traffic back home. It's absolutely unclear to me if I can design a robot that can engineer a set of rules to repeat this feat. And that sort of leads to one of the first messages, which is explicitly programming such rules is tedious. For instance, in self-driving, the right rule depends very much on what other humans are doing. But interestingly, we humans, every day on the road, are able to drive. So implicitly programming robots by imitating human driving seems like a right strategy. So that's one of the key pieces that I'll talk about. The second piece is that robots are not alone in the road. Take a look at this busy, unprotected left. It's full of pedestrians and cars. If the robot views these pedestrians simply as dynamic obstacles that it must avoid, it can never make that turn, right? It has to actively create an opening by negotiating with other actors and predicting how they will respond. So to do this, the robot has to understand the latent intent of other human actors and communicate their own intent to them, right? Okay, to make things a little bit concrete, let's quickly ground these problems in a more familiar and general framework of a Markov decision process. So to recall, an MDP is how we formalize sequential decision making. So you have, state, actions, rewards, or as I like to think, costs, and transitions. So the state here is the position and velocity, not just of the robot, but of every other human actor in the road. And the important thing is that the cost function, or the reward function, it's latent. We don't know what the reward function is. And we know some parts of it, but we don't know it in general. And we need to use imitation learning to recover this cost function that makes the robot drive like a human. Also, the transition function is unknown because it depends on how the state of the world of other humans evolve based on actions the robot takes. So we need to learn this function as well by predicting latent human intent. Okay, so yes.
And maybe you can repeat the question because you have the
yes.
next one. So maybe why do you want to imitate humans? Humans can be pretty bad drivers, right?
Yeah, that's a great question. So in this talk, when I talk about imitating humans, I talk about imitating our expert human drivers who are, trained specialists who are driving the car on the road. And perhaps that is a practical decision that we make in the industry that, the drivers literally determine the product. They're trained specialists. They know how to drive a truck. We just want our product to drive like them. And they know when their driving is not good, so they're able to curate out those bad demonstrations. But yeah, in the real world, it's a great question. We'll probably come to that at the end. When humans are not experts, it becomes a bit more tricky. Great question. Any more? All right, let's keep going. So with that, let's return back to the original picture. So today we'll talk about two challenges. First, we'll talk about imitation learning. So how do we interact with the human to learn the optimal policy? And second, we'll talk about intent prediction. How do we interactively forecast human actions conditioned on the actions that the robot takes? Okay, so let's begin with the first challenge of imitation learning. So I'll begin with a really simple problem that's actually inspired by real-world events at Aurora. So let's say you want to learn how to lane change, right? So on the left is our truck, and on the right we have two cars, and there's a slot between the cars. And the general idea is that you want to extract features that describe the road, that describe the scene, and you want to learn a function that says, should we lane change or not? Right, so it's like a straight-up binary classification. So it should be pretty easy. Let's think a little bit about the features. You might have what is the distance to the exit, right? Is there a disabled vehicle on the shoulder? How does traffic congestion look in the lanes? These are some of the features that you might have. Now, it turns out one day one of your interns come in and says, you know what? Let's also add a feature that stores the decision we made at the previous time step, because I think that's going to be a very useful feature. You said, why not? Let's add that as well. So you add in the past action, right? Whether you lane changed or not in the previous cycle. So a standard approach to imitation learning is called behavior cloning, which basically treats the problem as a supervised learning problem. There are three simple steps. First, go collect lots of data of humans lane changing. So in some cases, you see that the humans don't change a lane because maybe the right lane is blocked. And sometimes you see that they take a lane opening, and you go collect this data. You train a classifier that maps features to decisions. Again, it's a binary classification problem. And then you validate this policy on some held out data. And if it looks good, deploy, right? So you get an exciting Slack message from your intern one night. Oh my God, this classifier is amazing. It's got 99% accuracy. And before you say overfitting, I added regularization, so we're good to go. Right? So you are stunned. The intern is overjoyed. The team goes out for beers. Right? Next day, you test this model. You think, wow, 99%, this is going to be a great model. So let's say the truck is next to a car and decides to lane change. And you find that a bit odd because it seems like this actor is very close. Seems like a tight lane change, but whatever. It's 99%. It's good. So the truck begins a lane change, but the actor doesn't slow down. They're still going at a high speed, right? And strangely, your product doesn't abort the lane change. It just keeps going, right? Eventually, it almost runs the actor off the road, right? What happened? Why didn't the learner just simply abort the lane change when it looked dangerous? Can anybody take a guess? Yeah?
Because when humans aborted it, it only saw a no rather than the fact that they were going to do it and then they decided not.
Yeah, that's excellent. Right. Should have had you in our team. Yeah, that's exactly correct. So let's try to break down. So the answer was, I should repeat this. So the answer was that in the data, the humans never showed a recovery. They either made up their mind and never did the lane change, or they just did it. So just to dig into that a little bit, if you looked at the training data, again, you see these two clusters. It's either don't change, don't change, don't change, don't change, no, 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 or yes, 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 right? And what that creates this sort of strong correlation between the past action and the action at the current timestamp. And before you think this is a bug, this is not a bug. Humans drive smoothly. Of course, the past is correlated to the current action, right? So other than the rare transition points, most of the data that you collect have this sort of strong correlation between two consecutive timestamps. Okay, that's fine, but then what happens at test time? At test time, the robot just makes one mistake at the beginning, but once it begins to go, it latches onto that mistake and continues going. This is what we call feedback, right? We have this bad feedback loop. And what feedback does, it forces the robot into states that it has not seen at train time. So since there's no label for the state, the robot doesn't know how to recover. It's never seen a state where it's doing a lane change and things have gone bad, right? The humans never entered that situation for whatever reason. And so feedback drives a shift between the training distribution, right, where the human never made the mistake, and a test distribution, where the robot's clearly making mistakes and getting into these situations. We call this a covariate shift in the input, right? And theory shows that this leads to compounding errors, on mathematically known as O epsilon t square errors that grows quadratically in time. So feedback drives covariate shift. This is the fundamental challenge that differentiates imitation learning from mere supervised learning. And more concretely, if feedback breaks an assumption in machine learning, that data is IID. In fact, the data here depends on your learner. Your learner induces the state distribution it visits. Questions? Okay, cool. Now, in case you're wondering how common is this problem, it sounds made up. Let me assure you, it is a problem. So these are just 4 papers from self-driving companies and academia from the last few years that talk about this very issue. And it's not just the self-driving industry. So back in my postdoc days at UW, we built a whole fleet of self-driving cars called Musher. So this is a video of these cars driving around the hallways. And we were trying to program these cars ground up from imitation learning. So on the top right is Jonathan Spencer, who was driving around these cars providing demonstrations. On the bottom, you see a visualization of this learned policy where blue are good actions and red are bad. Okay, so when we roll the learner out, it looks like it's doing a good job until it crashes into the wall, right? It's the same underlying issue. It makes a mistake, enters a state that looks like I'm driving straight first into a wall, and oops, I haven't seen this state before. I'm going to continue, going straight and crash into the wall, right? So I'm going to continue making mistakes. Okay, so there seems to be a mountain of evidence for feedback driving covariate shift. So we thought, probably this should be reproducible in standard benchmarks that we use in academia, right? Turns out we are totally wrong. So we took benchmarks from imitation learning papers, simply ran behavior cloning for long enough to drive down optimization errors, and the learn policy turned out to be pretty good. The performance values were very close to the expert. So we thought, okay, maybe these environments are too easy. Let's try more complex environments. Turns out literature has time and time again showed behavior cloning does pretty well. In fact, I think there's a recent paper by Florence et al. That shows behavior cloning on these D4RL benchmarks is pretty comparable to most alternatives. Not the best, but it's pretty good. So this was puzzling, right? Just convinced you feedback is a real problem in self-driving, and our competitors have reported it. But on standard benchmarks, behavior cloning just seems to be fine. So what is the explanation? Is it to do with the data? Is it to do with the problem? Is it to do with the policy? Or something else is going on? So in times like this, we need clarity. And what better way to get clarity than to think about the infinite data limit, where, to take one part of the equation out of it. So we're going to take a slight detour. I'm going to convince you that covariate shift isn't just one thing. It's actually 3 regimes. Some are easy, some are hard, and some are just right. Okay. All right. So let's start with the easy setting. Here, the human expert is realizable. So with infinite data, you can make the error 0. For example, let's say you have a race car and you put it on a track. You see that the expert drives perfectly down the center of the track, right? And so shown on the left is the distribution that the expert induces. And if you have infinite data, your learner is just going to exactly drive down loss to 0. So you're going to see the 2 distributions match exactly. And so the solution for whenever you're in this regime, the solution is simple. Just go get lots of data. And if you do behavior cloning, life is good, and your policy matches the expert. And we conjecture that this might be the explanation that many of the benchmarks simply fall into this easy regime because the expert is either realizable or your network is expressive enough that it's able to explain the data well enough. Now, what if the learner is not, the expert is not realizable? And the expert doesn't visit all the states. For instance, let's say our learner, for whatever reason, can't perfectly drive down the center of this track. Okay? Once the learner spins out of the track, it doesn't know what to do. It's never seen how to recover, so it's going to keep making mistakes. Good analogy from Drew is, think of the expert as Roadrunner and the learner as Wile E. Coyote. If the expert never fell off a cliff, how will the learner know how to get back on, right? And this is precisely the flavor of the problems that we saw. The human was, for whatever reason, not realizable, and we didn't visit all the states. We call this the hard setting, right? So in a seminal paper, Ross and Bagnell showed that in this setting, behavior cloning has no hope. It's going to hit this worst case O epsilon t square error. Recently, our work kind of generalized this result. This is work with Gokul Swami that showed that entire class of off-policy methods. So, methods where all you have is, just a bunch of data and you have no interactive expert. This is the best you can do. So you might be wondering, okay, when does this setting occur? One signature of this setting is whenever the expert has access to more privileged information. So very quickly, this is true in self-driving because the human often has more context than perception can detect, right? Maybe they can look at a scene and tell when a driver is signaling them to go, and our just perception hasn't caught up to it yet. That's one place where it happens. Another setting is when you're imitating algorithms that are clairvoyant, right? Think of you're imitating an algorithm that has access to more information, the full model, and you simply can't do exactly what the algorithm did. So I had a string of papers in my PhD that really tried to analyze this problem and understand the consequences of this information gap. So this is another setting. Finally, there's this recent paper from DeepMind that talks about language sequence models, like chatbots, and shows that they too can fall into this category, where they create loops of self-delusion because their actions feed back into their next state and so on. So the hard setting is a very real, inescapable setting, and we need to deal with it. Okay. Questions?
So is it practical to include in the training data situations where your expert makes mistakes but corrects?
Yeah, it's a great question. I'll actually come to that in the end. And there'll be a setting in the middle where we'll do that set. But for now, let's assume that that's not the case. That the expert has limited expert support, so hasn't really made all this mistakes. But yeah, great question. Any more? Cool. Okay, let's keep going. So yeah, okay, great. There's a hard setting. What can we do here? Fortunately, there's a solution, and we have known this for a long time now, which is you have to interactively query the expert. So at a very high level, in a seminal paper, Ross et al. Showed a very simple meta-algorithm called Dagger, which iterates over 3 simple steps. Roll out your current learner. Go ask the human what the right action is wherever the learner visits. Take this data, aggregate it, and train the learner on the full data. And if you do these 3 steps over and over again, eventually the process stabilizes, and you kind of recover a policy that's pretty good, that has the best achievable bounds of O epsilon t. And recently we've generalized this setting. We realized Dagger is just one algorithm in the entire class of algorithms. And this entire class of algorithms, for example, algorithms like aggravate also fall into this setting. They all enjoy this O epsilon t guarantee. And they all look like, take your current learner, go roll it out, go ask the human what to do in this state, and go add this data to your data set. Okay. So if you're in the hard setting, you're out of luck. You need an interactive expert. You need to interactively ask the human, hey, I'm in trouble. What should I have done in this situation? Right. But is this really practical? To ask the human over and over to label situations that the robot visits. Think back to when we were all learning to drive. Imagine you were doing all sorts of crazy things, like going down the wrong side of the highway and asking your driving instructor, please help me. That's going to be a very petrifying experience for your instructor. And this is a real problem. It's unsafe for humans, especially, to give feedback to states where robot visits, and it's impractical. Instead, how can we learn from more natural human interactions? Let's say interventions. So let's quickly try to think about how interventions work, right? We conjecture that, let's say, humans have a mental model of a subspace of states that is good enough, right? As long as the robot is in this state, the human doesn't feel the need to correct. As the robot is about to leave this subspace, the human intervenes and drives the robot back into this region and gives back control. Okay, that's the high-level idea. How do we turn this into a mathematical algorithm for the learner to learn? We had a very simple insight, which is an intervention is telling us something about the human's latent value function. What do I mean by that? Presumably, in their mind somewhere, humans have a latent value function that captures the cumulative cost of taking actions and acting optimally thereafter, right? Every piece of intervention gives us a tiny glimpse of this value function. It's basically saying, is a state good or is a state action good or a state action bad? Even non-interventions, the fact that they're not intervening is telling us something, that the robot's probably in a good enough state. So we have a very simple approach called expert intervention learning, or EAL, that exploits this insight. So the way EAL works is we are going to model interventions as constraints on the latent action value, right? So let's formalize this very briefly. Let's say we are solving for an action value Q that maps state action to real values. So the lower the value function, the better. Given a set of expert demonstrations, S star and A star, sampled from P of expert, the objective is to correctly classify these demonstrations. For example, A star must belong to the minima of Q. The action human takes must be the optimal action. Next, as the robot executes the policy, we're going to end up with 3 types of constraints. Stage 1, when the human is not intervening, we can definitively say that the Q values are below some threshold, delta, right? Stage 2, when the human takes over, something bad happened, right? So at least for that state action, that had to be above this threshold, delta. And finally, as the human is recovering, they're acting locally in a locally optimal way. So you can specify that as a third constraint, and you put them all together, and you end up with this sort of constraint optimization problem, such that and which you can solve very efficiently in an online way to get a regret bound of O epsilon t. So this is as good as what Dagger would have given you. So this is as good as if the human had shown you corrections, you could have also you would have the same bound, right? Questions? Okay, cool. Yeah.
So, in order to implement this expert intervention learning, what do you actually have? Do you think for implementation of it, you actually have people who are monitoring the state of the robot, or does the robot have to self-identify when it hits this threshold that it's no longer within, say, its action here is less than this delta good that you've stated here?
Okay, that's a great question. The question was, is a human monitoring the robot and saying, whether the threshold was crossed or not, or is the robot self-reporting? In this work, the human is intervening, so the human's monitoring. Whenever the human intervenes, that act of their intervention, we call that time point when the Q value went above the threshold, right? But your question, I take your question that can we actually think about robots self-reporting when they think they've hit an anomalous situation? I think it's an interesting question, and there's some work that tries to essentially have a robot self-report when it hit an anomalous situation, ship that data to the human, and ask them to give feedback here. Was this bad or not? But in this work, we are not doing that here. We are having humans explicitly intervening. Cool. Okay.
Hi, I have a quick question.
Yes.
What is the latent action value function? What does it actually? What is the function?
Yeah. So in this work, the agent action value function was simply a 2-layer MLP that's trying to map state actions to values. There's some work that when we extended this work to settings where you kind of are trying to learn cost functions, then this Q value is parameterized as the per time step cost function, and then you can kind of approximate the Q value by summing up the cost over rollouts, right? So yeah, that's how we kind of parameterize Q.
All right.
Cool. Okay. Awesome. So how does this work? How does EAL perform on the robot? Well, so here you can see Jonathan kind of intervening as soon as the robot gets close to the wall, and then returning back control. So, he's continually doing this, and in the early trials, EEL is just like behavior cloning. Because of compounding errors, it keeps failing, but as it gets more and more intervention, it starts to get better and better. And just after 60 seconds of trials, EEL runs without any intervention at all, which is pretty cool compared to, how much time, how much effort Dagger would have taken. And yeah, on this particular setting, behavior cloning failed even after 24 demonstrations. So just a very quick quantitative look at quantitative plots, right? You can see EEL is able to drive down errors with much less queries. Behavior cloning plateaus, as we explained, and Dagger wastes a lot of repeated effort by querying humans in obviously good states. And the closest baseline was this algorithm called HG-Dagger, which is like EEL, except it only uses explicit feedback. It's not using this implicit feedback of no interventions means something good's happening. So we showed both practically and theoretically that this is throwing away some crucial information. So the way I like to think about this is EEL is trying to squeeze out as much juice as it can from the intervention signal, right? Okay, cool. So in the hard setting, we were able to get around this problem of non-realizable expert, but we required an interactive expert that we had to query on policy. But very briefly, we are going to talk about a setting in the middle, and this is in relation to the question that was asked earlier. So what if you still had a non-realizable expert, but one that was full support, right? So the expert visits all the states. Now, even in this setting, behavior cloning is pretty bad. Like it's, because there's still compounding of errors. But you don't need an interactive human expert in this setting. Instead, you can get by with an interactive simulator. And just with an interactive simulator, you can kind of hit O epsilon t error, right? Yes?
Maybe you're going to answer this.
Yeah.
But a simulator typically doesn't align well with the real world. Is that kind of the medium setup that you're talking about?
Yeah, that's you're advanced here. We're in a company, so we have money. We can make simulators. But Jeanette's asking a good question, which is, in the real world, no one gives you a simulator. We'll maybe, maybe not touch on this.
Wait, are you claiming Aurora has a simulator that is as good as the real world driving experience on an American highway?
It's good enough for what we're going to do.
Okay.
But not like, it has to be good enough, as we'll see. Good enough for the algorithm bounds to sort of work. So yeah, good enough simulator, let's put it with an epsilon. Yep.
In the robot example that you showed, the video, what was the input to the policy? Was it like a very high dimensional input?
High dimension image compressed, so just like an overhead image of like the occupancy map, and then that's kind of compressed. So the action space is a set of primitives that it can take, and the input space is just a snapshot of like its local map.
Can you explain again why EIL outperforms Dagger that much?
Yeah, so the outperform thing is with caveats. It's how many times EEL queries the human versus how many times Dagger queries the human to get with an epsilon performance bar.
Yeah.
So, yeah, so the idea is EEL is, okay, good. The idea is Dagger is querying the human even in states where it has a lot of labels, right? Because the Dagger algorithm, naively written, just says, roll out the learner and on all states go query the human. EEL is simply getting interventions. So it's getting queries whenever the robot makes a mistake. So it's like, imagine there's a bubble. Every time the robot leaves the bubble, it's only then is the human giving queries. You're not querying the human inside the bubble, right? Whereas Dagger is querying the human wherever the robot is. So that's the difference. Okay, good.
Quick question.
Yes.
How does EEL compare with like not reference and ranking-based policy? Like when you compare it to like, okay, this is a better policy than something that was previously seen, ranking-based in that sense, because you also like it seems like it's been running like it reduces the half space constraint on the Q function.
Yeah, I would say that if you had a ranking-based approach that's trying different policies, if we didn't actually compare EEL to preference-based methods that's showing two different policies and asking the human for feedback, I would say that I mean, it's kind of difficult to compare these two approaches because EEL is something that's running on policy, whereas you could, in theory, be super smart about exactly what two queries you choose to query the human to collapse uncertainty in an efficient way. But there are other challenges. For example, you would have to make assumptions about the how to choose two policies so you reduce entropy. So we didn't really compare with preference-based methods, but I think that's an interesting avenue to explore. Cool. Okay, sounds good. So I'm just going to blaze through this setting at a very high level. So the setting again is a medium setting. And we've been thinking about this for a while now. And the underlying idea is that you can use an interactive simulator to build the distribution that the learner visits. That's the high-level idea. So in this setting, the expert gives you a bunch of demonstration and then just walks away. By using the simulator, you're building the distribution the learner induces. And the goal is to simply match these two distributions. And you can think of them as specifically matching performance metrics, performance moments, to get an O epsilon t guarantee. That's the high-level idea. So, interestingly, there is an entire spectrum of moment matching algorithms in this setting that I'm not going to be able to go into details today. But on the right-hand side, you have algorithms that match what we call reward moments. So you're trying to find a reward function that discriminates between the learner and the expert. All inverse reward learning algorithms fall into this setting. Maxent IRL, Gale, we have our own algorithm, ADRIL, that minimizes IPM metrics. They all fall into this setting. The catch is, and it's not talked about, but you need a planning oracle that's able to explore all possible actions, so this exponential space, to figure out how to match trajectories with the human. So that's a catch. On the left, you have matching value moments. So the idea is you're trying to find a value function that discriminates between the expert and the learner. And we have an algorithm, Alice, that essentially does this. But the trick is you have to adjust for covariate shift. And you can do that by reweighting data using density ratio methods. And so you don't need to do planning for Alice, but you need lots and lots of samples to estimate the density ratio perfectly. And there's a whole set of things you can do in the middle where you can try to mix and match these methods. So you can do k steps of planning and then density ratio your terminal state to essentially get the robot to visit a set of states that look a lot like the humans, right? The nice thing is all of these algorithms guarantee this O epsilon t, which is in some sense the best you could do. But depending on how much samples you have versus how much time you want to spend with your planning oracle, you can choose some setting in the middle.
Sorry, could you elaborate?
So the planning oracle is any inverse reward learning method needs a planner. Given a reward function, it needs to find the optimal policy, right? So you need to call a planner that searches over all possible actions to give you the optimal policy. Okay. So that's what we call it.
So not in like the generative setting, like not in the Gale setting, like in the policy optimization.
Well, you can
setting.
say Gale is running policy gradients, right? But you can come up, and I mean, ultimately you can create MDPs where it has to visit every action of every state to actually find the optimal policy, right? Given a reward function. And that's kind of hidden, but that's a real price that you pay when you use this method. Okay, Any more questions? Cool. All right, so we could move on to the second half. So yeah, that sort of completes our story. We talked about this 3 regimes of covariate shift: easy, medium, and hard. For the easy setting, just go do behavior cloning. For the hard setting, you need an interactive expert. But the interesting setting is a medium. There's a lot of research in this setting. If you have a simulator, if you can somehow, if you have a dynamics model, imperfect ones as well, you have some hope of not querying an expert online, but still trying to estimate your distribution. Yeah.
So I guess following on the sim to real question, if you have, say, like a driving simulator that has good models of, say, how the other vehicles are going to respond, right, which would be something you'd need to have a good driving simulator, why wouldn't you just use that for like online planning or something like this?
It's a great question. I think you can ask. There's 2 different requirements of a good simulator to do implement these kind of methods, and something that's going to drive your car on the road. There's safety, verification, constraints when you're actually deploying the product on the road, which you may be okay with in the simulator. It doesn't have to get the crazy edge cases correct, but maybe your product has to. And so I think those 2 kind of separate. Yes.
The simulator model human intent.
Oh, pardon? Sorry, I missed your question.
Can the simulator model human intent?
Yeah, the simulator can. I mean, it can because So I assume by human intent you mean whether the human's trying to like lane change or not, or go ahead or not. Yeah. So the simulators that we use we call them smart actors, and they can kind of model human intent to respond to things that the human does, to what the robot does, right?
If the simulators model human intent, let's say a car avoid being swerved into, then why not just use what's the algorithm being used to simulate the intent?
That's a good question. The simulator kind of has a bit of an advantage. It kind of knows, it's created the setting. So when someone creates a simulation, the simulation sort of knows the scenario, knows the context. And so it's actually it's contrived enough where the simulator can actually, has access to a lot more information to, create intelligent actors. But it's quite different when you're out in the real world and you don't know what setting you're actually in, you don't know that you're in a contested merge or contested lane change, right? So then it can get kind of tricky. So in the interest of time, I'm just going to accelerate to the second half of the talk. So yeah, I think this set of videos just show that, the things we talked about today runs in the real world. So you have, we have on-road interventions that are then turned into simulations that then the model uses to make better models, and it works. And yeah, I mean, just quickly to touch on open questions. There are a lot of open questions, especially in the medium setting. For example, we're looking theoretically at what are minimax optimal algorithms. We are looking at something that's become increasingly important, which is the role of confounds in the data. Human has a lot of unobserved variables that influence their actions, and so, how do you do imitation learning under confounds? And I think there was a question earlier about what if your experts aren't optimal? What if they're suboptimal? So these, all 3 of these problems are pretty interesting, and we were kind of thinking about them. But yeah, in the interest of time, let's talk about the second half of the talk, which will be shorter. The second half is about intent prediction, which is how do we interactively forecast human action. So we talked a little bit about intent. We're going to formalize this in the second half. Okay, so like we did before, let's start with a simple example. That I really like, by the way, merges. So when we all learn how to drive, this is a very stressful thing, merging for the first time. How does a robot, how does a robot kind of negotiate a merge, right? So we have a robot truck in the right-of-way lane, and we have a car that's merging in. And let's say we've already solved imitation learning. So we already have a good cost function via imitation learning. Now we have to plan with this robot. We need to So to do that, we need to predict the future 5-second motion of what the other merging actor is going to do. And then we call, let's say, an MPC planner that computes the optimal trajectory. So really all we need is a good enough forecast of the other actor, right? How do we get such forecasts? So the traditional approach in industry is to treat forecasting as a cascaded step after perception and before motion planning. Recent methods have improved upon this by joining perception and forecasting in a differentiable end-to-end manner. But crucially, still today, motion planning is viewed as a downstream consumer of forecasts. So let's think through what will happen as a result of this, right? So let's say we go ahead and collect a lot of data to train our forecasting model. So in our training data, 50% of the time, the human merges after the car, and 50% of the time, the human merges before the car. We then train the latest, greatest forecasting model to predict the future. This is what we get, right? This forecast looks like it has just huge, it's like a big blob in front of the truck, right? It has a huge variance, and the planner looks at this, freaks out, and says, oh my God, I have to brake to avoid this blob. What happened?
The planner was like predicting for like a worst case scenario of where like this variance is going to be like closest to the truck, and so it's trying to avoid the largest distribution of where it's spread.
So the answer is the planner is trying to avoid the worst case scenario, which is great. But why does the forecast look so terrible?
The planner is not taking into account that the human will react to its behavior.
Yeah, okay. So you all should help us. Great, yeah. So as you might have guessed, there are two distinct modes in the data, right? There's mode A, where the robot merges after the car. And there's mode B, where the robot merges before the car. And when we just train the forecasting model, we marginalize over what the robot's doing, right? And so we get this distribution that's sort of marginalizing over these two modes and then predicting this huge variance. And as a result, the planner freaks out and brakes excessively. So yeah, the key observation, as you pointed out, is that the robot, what the robot does depends on other humans, but what humans do depend on the robot. And so this turns into a chicken or egg problem. To do planning, you need forecasts, but to do forecasting, you need the plan. You need what the robot's going to do. So here's an urban example of the robot taking an unprotected left turn with vehicles, bicyclists, and pedestrians. And again, the same situation that we saw before comes up where, the robot's motion depends on what the actor turning right is going to do. The actor turning right is looking at other pedestrians, and there's this oncoming car that's not sure what we're going to do. So there's this huge, complex dependencies that involve the robot in the middle. So I guess the observation is that all actors in a scene influence each other. And the robot is simply an actor that we get to control. But there are other humans in the scene. So in some sense, as you might have intuited, we need to jointly reason over all the actors to forecast them as well as subsequently compute a plan. All right. But wait. The space of joint trajectories is pretty big. Like, think of a single trajectory. That's a continuous sequence of t-dimensional vector of waypoints. Now you have n actors, so you're talking about a combinatorial space of futures. And moreover, this still is not addressing our chicken or egg problem, right? Unless you want to forecast the planner, which is a different discussion. So our key insight is that made this problem tractable is that it's actually misleading to think of a continuous space. There's actually an underlying discrete grammar that we are reasoning about. And we call these grammar modes. So it's pretty simple. There are three fundamental modes. Given two actors, you look at their forecast and you say, either they're going to have some conflict, and if so, somebody goes first, or they're not going to have any conflict. So A yields to B, B yields to A, or A and B just don't yield to each other. And it turns out, and this is work with McCall at Aurora, that pretty much all of self-driving can be described using this fundamental discrete grammar. So, for instance, take this merging scenario that we looked at before. You can say something like, you can describe the scenario really well by saying, the robot R yields to A, and this actor B yields to R. Let's say I knew this is the mode that we want the future to be in. If we know this, knowing this mode, we can actually forecast all three actors, and a single mode corresponds to a single basin of forecasts. So, more generally, if you were to write down the value function for all three actors, that value function is multimodal, but specifying the modes, saying R yields to A and B yields to R specifies a single mode of that value function. Right, and this works for more complicated scenes as well. So let's say we are lane changing simultaneously with other actors. Knowing the mode defines the slot that the robot gets into. And in fact, the forecasts need only be accurate enough for the robot to safely and predictably get into that slot. Okay, so how do we infer what modes various actors are likely to choose based on choices by the robot? So let's look at the scene before, and let's abstract it away with a graph, right? Imagine each actor as a node in the graph. The edges of the graph tell us relationships like, is actor A yielding to actor B? So given a set of decisions made by the robot, or modes chosen by the robot, we are going to infer what modes other actors likely are choosing. And we're going to do this by passing messages. So for instance, we can look at the scene and say that the actor turning right wants to yield to both the pedestrians, and as a result, the robot must yield to this actor. And finally, the oncoming car is actually turning left, and so it'll likely not conflict with the robot, so they should both not yield to each other. And the nice thing is, once you've figured out this mode, you can forecast each actor independently given modes. And once you have the forecast, you can go ahead and call your favorite MPC algorithm to get a plan. So the way we generate this is by, we put this together using a multi-stage graph neural network, which we call geometric transformer net. So the transformer here refers to the aggregation step in the graph neural network. So the high-level idea is that you have a graph neural network where the input are node features, state and history of each actor, and edge features, transforming one actor to another frame. We then encode these features and do k rounds of message passing. And then there are two outputs. What is the mode that each edge corresponds to, and then predicting t-step futures for each actor in the scene. So, and so when you put everything together, this is how the scene kind of plays out. We can see that by reasoning about different modes, the robot's able to kind of confidently go through this intersection. It's also interesting in this scene, you see a cyclist suddenly pop out from an occlusion. And that means that this inference has to be running rapidly in real time because it has to detect this actor, figure out what mode it belongs to, and then forecast its future within 10 hertz, right? Okay. Questions? Yeah.
Is there a reason that there's no mode for yield when both yield to each other and kind of get at a standstill?
Yeah, that's a great question. we often don't, we're often, at least at this point, we're not modeling places like yield where two actors come to a stop because they're not able to communicate. I think we're trying to, the way we think about the scene is that, there's a flow of traffic, and for that reason, eventually the modes resolve themselves and falls into one of the two basins where one actor goes and the other actor stops. Yeah, certainly you can have intermediate states where two actors both might be stopping to each other, for example, at always stops. But yeah, right now we don't model it.
The modes that you're modeling, are they sort of described by human engineers deciding what these modes are, or are you extracting that somehow from a bigger trajectory forecasting distribution?
Yeah, so we have data. I think the way we extract the modes is you look at 10-second future, then you have an auto labeler that figures out what happened, what mode was followed, and then that's used as a source of label.
So I think if you have a complicated scene and maybe you observe it 10 times, let's say, maybe it will not always be the same set of modes, but maybe there's like two kind of possibilities how it ends up, right?
Yeah.
It looks to me at least that this specific architecture can only ever predict one mode, right? So do you think there's any work on an architecture outputting multiple sets of modes with maybe some kind of probability?
Yeah, so actually what I said is the architecture outputs a probability for each edge of yielding or A yielding to B or B yielding to A. So there is a pairwise independence joint distribution that it's modeling, but you're right. It can happen that you need to capture multiple possible interactions that can play out, and then that's some active work that's going on. But just doing this gets you a lot of mileage, so yeah. I think we're running out of time, so I'm just going to skip to the end, unfortunately. This is, there's a lot of cool videos of this sort of, intent prediction working across various scenes. I just want to end quickly to go back to the picture we laid out initially. So looking forward, so I talked a lot about self-driving, but in my lab at Cornell, I'm going to be going back to personal robots. And I want to bring some of these insights from self-driving back into personal robot space, which I think is far more challenging and far more open-ended. But to talk about, some of the directions that I'm interested in. So we talked about learning from natural human interactions. I think, in the personal robot space, there's just a lot of questions. For example, what are good task representations for few-shot learning? How do we learn from multimodal feedback? Learning with causal confounds like trust and adaptation. And I think, having some answers to these questions is super critical for personal robots. And for the second challenge, planning alongside human partners. We talked about discrete modes for self-driving. That was easy. What are modes when two humans are, doing whole body manipulation near each other? I don't know. How do we communicate intent to collapse uncertainty? How can robots plan safe, predictable motions? So, look forward to tackling some of these challenges in my lab. And lastly, I would like to acknowledge the amazing co-authors and collaborators in the work I presented today. Particularly, I would like to acknowledge the entire team at Aurora, who worked tirelessly to make the amazing product we have today. With that, I have to take questions.
Thanks so much for the great talk. Are there any more questions? We have time for a few.
In that last slide, you kind of talked about future directions for these personal planners. Is there, in your lab and your research going forward, are you looking to try and dabble in all of those fields, or is there anything in particular that interests you that you're looking to work towards?
Yeah, that's these challenges are very open-ended. I think right now my focus is still very much imitation learning. Particularly right now we're looking at causal confounds because it's a problem in self-driving, and I suspect it's a problem in any robotics where humans have a lot of latent variables. That's what I'm focusing on now. One of the things I would like to start with as I move from self-driving to mobile manipulators is representations. Representations in self-driving are a little bit. The community has thought about it for a long time, but for manipulation, I think how we represent modes is pretty challenging, but it's key if we want robots to work seamlessly alongside humans. I think that's the thing that we'll probably start with.
sorry, you.
So if you're focusing on natural human interactions, like a lot of what we learn, like let's say you're on the road and driving, a lot of the interactions between like someone in a car and someone in another car are similar to what we see in just like normal non-driving interactions. Would you take any of the like models you develop or what you learn from natural human interactions and apply that back to the self-driving field at all, or?
Yeah, that's a good question. So for self-driving, ultimately, you only need to model enough so your product drives like a human. It doesn't necessarily need to have the nuance. It turns out, from after years of looking at this, the nuance with which you and I might, infer how the scene evolves, like someone's, doing road rage. The robot doesn't need to infer to that granularity. So you can get to a product without getting, inferring to that level. I'm pretty sure that's not the case for personal robots, perhaps, because they're interacting much more up close with humans. So probably not in self-driving. Probably it'll go the other way, where you try to take some of these insights and try to simplify the personal robots problem and see where to go from there. Yeah.
Can robots also reason about kind of the perception that other actors in the road have? For example, if you're following a car and you see that suddenly it swerves out of its lane or slows down, then you could infer that there's an obstacle before you can see it. But is there a way that it could do something like that?
Yeah, and that happens a lot. For example, construction. Sometimes you don't see construction, but the robot's reasoning. And we are actually working on that in our model at the moment. You can infer that. You can infer based on the emotions that there's some object there that's correlating what all the actors are doing. They're all suddenly lane changing. So that's something that we're modeling at the moment.
In self-driving data sets, coming across situations where something dangerous happens or where an accident happens is really, really rare. When you train these models, do you do anything like upsampling situations that you deem to be dangerous to make sure that your model is accurate in very, very rare situations?
Yeah, excellent question. That's right. If you take, you have to, you can't simply do empirical risk minimization because 99% is boring. You have to, create clusters of data points that, and make sure your model's good across the board. The second thing I want to say is that if events happen rarely because humans are really good at guarding against events and they get out of situations. And so that's really a key thing the robots have to learn, how to guard like humans so they don't get into those trouble situations. I think that's the key piece that makes the product possible.
With that, I want to thank you again for coming in person to give a talk at the Stanford Robotics Seminar. Thank you again.
Yeah, thank you everyone. This is awesome.